Hi everyone. Today I'll be teaching about process state diagram. A process state diagram shows the life of a process through all the states that it can visit in its life. Now there are three ways to draw a process state diagram, each with increasing level of complexity. The first we'll start with is a two-state diagram. Now a two-state diagram is a relatively simple process state diagram which includes only two states. As the name suggests, those are the not running state and the running state. A process will first enter not running state, then it will be scheduled to run state, and from there if any interrupt or timeout occurs, then it will go back to not running state. At not running, there will be a queue of processes waiting to get to running state, and at running state there will only be one process at a time. The processes will be scheduled or dispatched from not running to running state, and from running to not running they would either be interrupted or they will face a timeout. Now main points regarding two-state diagram is that number one is scheduler sends one process at a time to running state, and the other main point is that after interrupt process goes to not running state and another process is sent or is dispatched or scheduled to running state. This process is called dispatched, and this is done by a scheduler. So it's a relatively simple way to understand the life cycle of a process. It just goes between not running and running. Now the other way to draw a state diagram is the 5-state diagram. It has 5 states. The 2-state diagram is way too simple to express the complexities that are involved in the life of a process. So in 5-state diagram we add 3 more states. What those states are, what would we do is we would divide the not running state into 2 sub states, the ready state and the waiting state, and we'll add 2 more states, the new state and the exit state. What all these are, I'll explain in detail. So first, the point is that in this not running state is divided into 2 substates. They are, the number one is ready state, and the second one is waiting state. So first we had not running state and running state. Now we have 3 states: ready state, waiting state and running state. The running state remains the same, whereas the not running state is divided into 2 parts, the ready state and waiting state. Second point could be For good measures, we have added two additional states to a process. They are new state, and the second one is exit state, or it could be called as halt state or terminate state. So far what we did is we split one state into two parts and added two new states. So let's draw the state diagram for the 5-state diagram. And in this the running state will remain same, since we changed nothing with the running state. We just split the not running state into two parts. Those are ready state and the waiting state. We added two new states. First one is the new state and the second one is exit state. The process will come from new state to ready state. The process here would be admitted from new to ready. From ready to run, it will similarly as in last time will be dispatched or scheduled. Now here we added two states because the last time we went from running state to not running state when either interrupt occurs or timeout occurs. Here, if the interrupt or timeout occurs, we went to ready state, but if in the event an input output is required, last time we went straight to not running state. Here we'll go to wait state, and there the input output will occur, and we'll go back to ready state once the input output is complete. And when the process has completely terminated, we can straightly go to exit state. Now the process from new to ready would be admitted. This is because new state is in secondary memory and the ready state is in primary memory. In fact, these three states are in main memory, and the new and exit state are in secondary memory. So what this does is that we can have a lot of processes, but they would be in secondary memory, and when we require them to be brought into main memory, then we can have them in ready, run, and waiting state. That would save a lot of space. Memory is more expensive and is less available than secondary memory, so we bring them into main memory only when it's required. Otherwise they'll stay in the new state. When they are ready to be execution, then they are brought into the ready state. From the ready state to running state, they are scheduled or dispatched by the scheduler. Now from running state to ready state, they will go either when interrupt occurs or timeout. From running to waiting, as I said before, waiting is for input output. So if an input output event occurs, they will go from running state to waiting state, and when input output event is completed, they'll go from waiting state to ready state. When the process is completed, it will go to exit state. Now the questions that came in previous GATE exam as to number of processes in each of these states. So let's see that in ready state, there is the queues. There can be n processes in the ready state at a time. Similarly, in waiting state too, there can be n processes, but this is the important bit, that in running state, there can only be one process at a time. Only be one process in the running state if your computer is uniprocessor. If it is given in the question that there are more processors in a computer, then there can be as many processes in the running state as many processors in your computer. Now let's learn about these states in detail. New state. A process when created, it is in new state. Until it is ready to be executed, it will stay in the new state. So we'll write, if any process is in creation or either have been created, then we can say that process is in new state. That's all about new state. The second state is ready state. So once a process is ready for execution, then that process can make a transfer from new state to ready state. That would be the first point. Once a process is ready for execution, then that process can make a transfer from new state to ready state. The name for the transfer here was admitted because it is coming from secondary memory to now main memory. We can also write about ready state is that as I told before, there can be multiple number of processes in a ready state. In fact, there is a queue in a ready state. So at a time, multiple number of processes can be present in ready state. Now, the process can be multiple, but they can be finite, and the ready queue is there can be one ready queue for every processor in the system. So each processor has its own ready queue. So for example, if this is a uniprocessor system, then that would mean there is only one ready queue. And if it is a multiprocessor system, assume there are n processors, then it will have n ready queues. Now the third state is running state. It is similar to what it was in the two-state diagram. A running state, there can only be one process which is running. So let's write that. Among finite number of processes in ready state, only one process is selected at a time and scheduled onto the CPU. This is done by the scheduler. As I said before, there can only be one process in the running state that will be selected by scheduler and will be sent on to the ready state one at a time. we can write that as it means that only one process can be present in running state at all times. But this is similar to, this depends on the number of processors that you have in your system. So if it is a uniprocessor system, then there will be only one process in running state, whereas if it is a n processor multi-system, then there would be n processes in the running state. And the last point could be about the timeout. So we can say that while one process is in running state, if any interrupt or timeout occurs, process can make a transition from running to ready state. Now the fourth state is waiting state. As I told before, waiting state is for input output operations. So the first point is, while one process is in running state, then it requires some input output operations then it can make a transition from running state to waiting state. The next point is, in waiting state, multiple number of processes can perform their input output operations parallelly. Now, as said before, there can be n number of processes in waiting state. The next point is, once a process completes its I/O operation, then that process can make a transition from waiting to ready state. Now the process simply won't go from waiting state to running state. It will first have to go to ready state and then wait for its turn to go to running state, as some other process would be running at that time. Now the last state, the fifth state, is exit state. So we'll write, once a process is completely executed. We mean by completely executed as in it has completed the CPU operations plus IO operations. Then that process can make a transition from running to exit state. What it means simply is that it will empty its main memory and go back to secondary memory. Now there are some things that need to be remembered, so I'll write them as notes. The first is, at any time, if any process is existed either in ready state, running state, or waiting state, then that process is said to be existed in main memory. This I also showed in the diagram, where this circle represents the main memory. So these ready state, waiting state and running state, these are stored in the main memory, whereas new state and exit state, these are in secondary memory. And there's one more important point. At any time, the number of processes that are present in main memory is said to be degree of multiprogramming. So that was a 5-state diagram. Now let's see a 7-state diagram. 7-state diagram, we add 2 additional states to a 5-state diagram. So this is a 5-state diagram, and we'll add 2 states. Those are suspended ready state and suspended wait state. One more important thing about these states is that they would not be in main memory, they would be in secondary memory. So a suspended ready state and a suspended wait state. Going out of main memory to secondary memory is called as a swap out. Similarly, going from secondary memory to main memory is called swap in. Similarly for suspended waiting, swap in and swap out. We can write as in this, we have 2 additional states. Along with the other 5 states from 5-state diagram. They are, number 1 is suspended ready state, and second is suspended waiting state. Now let's see what each of these are in detail. First one is the suspended ready state. We use these suspended states when we have no location in main memory left, so we want to make some space. The suspended ready state, so first point is a process can make a transition from ready to suspended ready when there is no vacancy in ready queue. This operation is called swap out operation. What that means is from main memory to secondary memory. The other point can be once a suspended ready state process finds some vacancy in ready queue, then that process can make a transition from suspended ready state to ready state. This operation is called swap in operation. So that was all about suspended ready state. Now let's see the suspended waiting state. Now the first point would be similar. A process can make a transition from wait state to suspended waiting state if there is no availability of input output device. There the ready queue was filled, but here the input output devices is filled. This operation similarly is called swap out operation. Now again, once it's suspended waiting state process finds some IO devices free, then that process can make a transition from suspended waiting state to wait state. This operation is called swap in operation.